Hello and welcome back. So we've been talking about ROC curves and PR curves, and I hope you have a good understanding of how they are generated. What's more important is trying to understand the relationship between an ROC curve and the corresponding PR curve. So if you plot the ROC curve for a given classifier, then we've already discussed that on the x-axis is going to be the false positive rate, which is the number of false positives that are generated out of all the negative examples that are given. And on the y-axis, then you have the true positive rate or the sensitivity, or it is also called recall. And then that is going to be equal to number of true positives divided by the total number of positives that are in the test set. Whereas in the PR space or the PR curve, we plot on the x-axis, we plot the sensitivity or TPR or recall as it is called. So that's where the name comes from, which is the same as what is being plotted on the y-axis of the ROC curve. Whereas on the y-axis of the precision recall curve, we plot precision. So precision is equal to the number of true positives out of all the positives that are predicted by a given classifier. So let's say if you have a classifier that predicts 10 true positives but it also predicts 100 uh, positives in total, then the precision that you get is going to be 10%, right? So that's a pretty low precision because we are generating a much larger number of positives and only a small percentage of them, about 10% of them, are actually positives. That's where these numbers come from. So let's talk about two algorithms. I'm going to call them classifier C1 and classifier C2. I'm going to use different colors for these two different classifiers. So allow me to switch to a different color here. So if you plot the ROC curve for, let's say, uh, classifier 1, so this is classifier 1, I'm going to just say that the blue line that you see is classifier 1, whereas the green line, let's use another color, let's use orange, that is going to be plotted in as C2. Okay, so let's say if we plot these two curves like this, and we get these two to match up at the end. Okay, so let me switch back to blue. Oops, blue. Okay, so let's say we've got these two classifiers. Now the question I'm going to ask, which one of the two is better? And I want you to pause the video and think about it. What this plot shows is that the orange curve for C2 is always higher than the corresponding curve for C1. So at all values, at all operating points, at all values of sensitivity or false positive rate, classifier C2 is better than classifier C1. So we go ahead and say that C2 dominates C1 in the ROC space. So the ROC curve for C2 is better than C1, and the area under the ROC curve for C2 is higher than the corresponding area under C1. So let's say if we are designing an experiment in which we have two different classifiers or two different features, and we want to see which of the two is better, then what we can do is plot their ROC curve. And if we see clearly that the ROC curve of one of them dominates the other one, we say that the one, in this case, C2 is better than C1, and that's going to be the result of our experiment, right? If you map these over to the PR curve, if a curve, if a classifier, let's say C2 in this case, dominates C1, okay, let me use a different color again. Okay, so if a classifier C2 dominates C1 in the ROC space, then it's going to dominate the same classifier in the PR space as well. So the corresponding curve for these two algorithms, the PR curve for the classifier C2 is always going to be give you better recall in comparison to better precision recall curves in comparison to C1, right? So that's the point that you need to understand. Okay, so it's going to dominate. It's going to be better than the other curve, right? So that's the first point, if a, that you need to understand. And the other point that I want you to understand is if a classifier dominates within this region of the ROC curve, then it's going to dominate the other classifier in the PR space by a significant margin in case the number of negative examples is much larger than the number of positive examples. So in case of data imbalance, this is the area that you need to pay attention to in an ROC curve. So let's say if the ratio of positive to negative examples is 1 to 10, and we see that a classifier dominates another classifier within this region where the false positive rate is low in the ROC curve, then the corresponding in that curve, that classifier is going to dominate the other classifier in the precision recall curve. Okay. And that stems from the fact that false positive rates, the, the smaller the number of false positives we generate, the higher the precision is going to be. But if the number of negative examples is much larger, then the denominator is going to be much larger. So we really need to pay attention to very small false positive rates in the ROC curve, because that is the place where the precision is being determined. So this region over here is where we should be looking, especially in uh, case of data imbalance test sets. So if you've got a problem, if you're shown an ROC curve and you see that one of the classifier dominates the other one at very low false positive rates, and you know that the number of negative examples for that test set is much larger than the number of positive examples, then you can safely assume that the precision of the curve of the classifier that dominates the other in at low false positive rates in the ROC space is going to do better in the precision recall curve space. So the AUC PR of such a classifier is going to be much higher, uh, and it's going to be much more precise with a higher value of recall. So I hope you understand and are able to relate these concepts. I will summarize these for you on the slides as well. There's a one-to-one correspondence between the two curves. So you can map each point in a ROC curve to a corresponding point in the precision recall curve. And so there's going to be a one-on-one mapping between the two. And we've discussed that in our on how an ideal classifier where it is located in the ROC space and where it gets mapped to in the precision recall space. And we've also talked about if a curve dominates in ROC space, then it dominates in PR space. And vice versa, if a curve dominates in PR space, then it dominates in the ROC space. Now, there are two trick questions that I want you to think about, and those are related to the behavior of random classifiers in the PR curve. Can you plot the PR curve of a random classifier, so a classifier that generates random numbers as its predictions, so a completely useless classifier? Can you plot its precision recall curve? And I welcome you to go ahead and try that out so you understand that unlike an ROC curve where a random classifier is going to give you a straight line smack in the middle, for a PR curve, you are going to get different curves depending upon how many negative examples there are. So the area of a random classifier, the area under the PR curve of a random classifier is not going to be zero point 0.5. It depends upon how many negative examples there are. And the other thing to understand, or another question that I would like you to think about, is what part of the ROC curve impacts the PR curve more. Okay. And one thing that you should realize when using PR curves is that they are really good in for evaluating performance or evaluating precision when the data set is imbalanced, unlike ROC curves, but they are not as aesthetically pleasing, or they are not as easy to interpret as ROC curve, because they can go up and down, and that is because how precision behaves as we change the threshold for classification. Okay, so that's one of the reasons. Similarly, you cannot average areas under the you cannot average ROC curves, sorry, PR curves, much like you can, as you were able to average the results of ROC curves, especially when the number of examples is different. So if you have, let's say, two different data sets, or that have a different number of positive and negative examples, you can calculate and compare the ROC curves of those two classifiers for those two test sets. But because the number of negative examples are different between these two, in the example that we are currently taking, you cannot compare two classifiers, the areas between these two cases for a given classifier. So I hope that helps you understand the relationship between the ROC and PR curves. If you want to read more about it, I really welcome you to read this paper, the relationship between precision recall and ROC curves. To understand a bit more about ROC analysis, this is a really good paper. I'll be posting these links in the for as reading material, and in the book you can also find a section dedicated to precision recall and ROC curves. Next, what we are going to try to do is to use code or how you can very easily calculate precision recall and ROC curves. Okay. So you've got, if you want to calculate ROC curves, you can use this help. And I'm going to show you a notebook where we've already done this. And sklearn already implements both the calculation of both ROC curve and PR curves. The important thing to understand and remember is that both of these curve functions, both of these functions that calculate the ROC curve and the precision recall curve, for a binary classifier, take the true labels, which are y. So these are going to be labels +1 and -1 for a given classifier, right? For a given machine learning problem. So these are the true labels for a given test set. So these are the true labels, and they can be +1, -1, or they can be 1 or 0, depending upon what you're dealing with. However, for the other thing that goes into these curves is the score, the prediction score, and not the predicted label. I need to emphasize that point because a lot of beginners make that mistake. They use the predicted labels in the calculation of the ROC and the PR curves. That's wrong because that only gives you the performance of the classifier at a single operating point where you have already discretized your raw scores or prediction scores for your examples into prediction labels. What you should be using is true labels, which are Y, and the prediction scores for the corresponding prediction scores for those examples. So if you take a look at these functions, let's say if you have a precision recall curve function, then you pass it the true labels. So this is going to be the true binary labels. And then you need to pass prediction scores, which are real numbers. So these are prediction scores, not prediction labels. Okay, not labels. Okay, so please don't make that mistake in your analysis and when you're using these curves in practice. Okay, so there are also other types of the type of matrix available for performance evaluation in sklearn. There's something called F measure. We've talked about that briefly. There's something called Matthews correlation coefficient. You can also calculate confusion matrices, and you can also calculate some multi-class matrix. And to do that, I welcome you to read this link. And what we are going to do now is we are going to try to understand these using a notebook, right? So I'll post this notebook as part of the module. This is simply a plotting function that allows us to plot. We've been using the same function earlier as well. We've got a function that generates a dummy example or a toy example. So it's going to generate a set of positive and negative examples. And then this is the bit that is interesting to us for now. From sklearn.matrix, we import the ROC curve, we import the corresponding PR curve, and we calculate the ROC AUC score, which gives us the ROC AUC score, the area under the ROC curve. So what this does is that does a numerical integration of the area under the curve to calculate the area under the curve for a given ROC curve, and you can calculate the average precision score for a precision recall curve. And what we've done over here is I've given you the function that if you pass it y, which is the true labels, with the corresponding prediction scores, which are in z, it goes ahead and plots the ROC curve, calculates the area under that, and then what it does, we have a very similar function that calculates the average precision as well as the PR curve. So area under the precision recall curve is typically replaced with average precision scores, and those would be printed. So what we do next is we use a classifier over here. Um, okay, and we use a support vector machine, first generate some data. And then what I do is I go ahead and use this train test split function, which randomly splits the given training data set. So these are the features X, and then we have the corresponding labels Y. These are the true labels for the given data set. And then I use a test site of point 0.2. And what that does is that it creates or it partitions these training examples randomly. If I use shuffle is equal to true to give me a training data set, XTR, and the corresponding YTR, which are the training labels, and it gives me a validation data set, XV, which is then going to be 20% of the overall training or overall data set that I gave as input. So let's say if there are 1,000 examples in X, and if I set test size is equal to zero point 0.2, then I'm going to end up with 200 examples in my validation set. So this is going to be XV, and then I've got the corresponding labels for that. Then I use my classifier at a certain value of C. I use a certain kernel. And then what I do is I train that classifier, and then I generate the decision function scores. Notice that I've used decision function scores and not the predicted labels. Then what I do is just to calculate accuracy at a given value of the threshold, I calculate the value of, I calculate the predicted labels by converting the scores. If they are above the threshold, I convert it to +1, and otherwise I convert it to -1, and that is what this code does. And then I compare the predicted labels to the given labels, which are in YV for this validation set to calculate accuracy. So this function over here gives you accuracy. And then at the same value of the threshold, I can calculate the precision, the true positive rate and the false positive rate. And I can also go ahead and calculate precision at that. So these are the formulas, these are the implementations of the formula that we have been talking about. So for a given threshold, you can go ahead and calculate the sensitivity, specificity, the false positive rate and the precision. And I welcome you to play with changing the threshold and seeing what the impact of changing that threshold is going to be on these metrics. So how does the TPR change when you change the threshold? How does the false positive rate change when you change the threshold? So you are welcome to try that out. But I can also calculate the ROC curve and I can plot that. So these are the two labels. And then I use the CLF.decision function to calculate the scores for a given set of training examples. So I can plot the training ROC, and then I do the same thing for the validation examples. So that is being done over here. And then I go ahead and calculate the PR curves for the training data set. So how does the classifier perform over the data set that it was trained on, just to get an idea. And then I also plot it for the validation. Okay. And then we also plot the surface the decision surface. So as you can see, this is the plot that we get. So on the x-axis is threshold, on the y-axis is the performance metric. So we plot the false positive rate and the true positive rate, which are indicated in blue and orange. So on the x-axis we have this threshold, y-axis shows the false positive rate and true positive rate, and as you can see, these are monotonically non-increasing functions. So for a given value of the threshold, we can go ahead and calculate what's the exact true positive rate and the false positive rate. And this gives us the first curve that we've been talking about when computing the ROC curve. And if I plot, and this is done for the training data set first, and then I can go ahead and plot we can plot the ROC curve, which is essentially a plot of the true positive rate at a certain threshold against the corresponding um, false positive rate. So we get this curve. This is the ROC curve. And we can do the same thing for validation examples. So this is the set of validation examples. We first plot the threshold. We plot the true positive rate and false positive rate against the threshold. And then we can go ahead and plot the ROC curve. And we can calculate the area under these curves, which is written over here in the title. So for the training data set, we get ROC AUC of 0.91, which is pretty good. The ideal classifier should have an area of 1.0, so this is pretty close to that, so that's pretty good. And then, but for the validation data set, we see that the validation AUC ROC is 0.77, which is actually lower in comparison to the training AUC ROC. So this is what we call a bit of overfitting going on. That is, the classifier has memorized the training data set better than it is able to do on validation examples or examples that it has not seen in its training. So this shows that the classifier is it's able to memorize better than generalize. So there is a bit of overfitting going on over here. Similarly, what we can do is we can also plot the precision versus the recall. So this curve over here that you see on your screen right now plots the precision in in orange against different values of the threshold. And as you can see, it can go up, but it can also come down at different points, unlike the false positive rate and true positive rates, which were non-monotonically non-increasing functions of threshold. So if you plot threshold here, you can plot the corresponding precision and recall at those values of thresholds. And then what you can do is you can get a precision recall in which the recall is on the x-axis. So this is the true positive rate, and on the y-axis you've got precision. So the area under the precision recall curve for this particular classifier over the training data set is 0.89, and we can also plot the same the PR curve and the precision versus threshold and recall versus threshold curves for the validation test set or validation set that we have for this classification problem, and we can see that these curves look like this, and then I can plot one versus the other. So this is the PR curve on your screens, and we can calculate the area under this curve, which comes out to be 0.86. So if you, if we can also go ahead and plot the decision boundary. One of the classes is shown in the middle, the positive class is shown in the middle, whereas we have a sufficiently large number of negative examples which are on the outside. And so this is a linearly non-separable data set. And we have been able to use this support vector classifier with an RBF kernel to get these numbers. But the conclusion from all of this experiment, although the goal is to help you understand precision recall curves and ROC curves, but one thing that we have noticed is that for this particular classifier, what we get is it gives much better training accuracies in comparison to validation accuracy. So there is a bit of overfitting or a bit of memorization or a bit of loss of generalization going on. So I hope this example and the coding exercise helps you implement these in your assignments and in your projects on machine learning. And if there are any questions, please let me know. Thank you.